Computations on types. In this section, we're going to take a look at manipulation of types and type lists, template metaprogramming, metaprogramming utilities in the standard library, and the type value encoding idiom. Let's begin with the first video, metafunctions. In this video, we're going to take a look at the idea behind type manipulation, metafunctions, and some useful use cases. C++'s type system is way more powerful than it seems. Values can be encoded into types, and types can be encoded into values. By using templates and constexpr, functions that perform arbitrary computations on types can be implemented. This can lead to more generic and safer code, to the creation of embedded domain-specific languages, or to optimizations and richer code thanks to expression templates. Here's a very simple type manipulation, turning a type into a pointer. Imagine that you're writing your own myVector class that takes a template parameter t, and inside you're simply creating a buffer of type t star. Given the type t, we're transforming it into t star, which is a pointer to t. This is a trivial transformation. But what if we need to perform the opposite transformation? That means that given a t star, we want to get t back. Templates allow us to implement functions that operate on types, and these are commonly called metafunctions. Here's a possible way of implementing the remove pointer function that we just mentioned. First of all, we're going to have a template class called remove pointer, which takes a single parameter t. Then we're going to specialize it on t star, and it will provide a type alias called type that given t star will evaluate to just t. So it's going to remove the pointer. Then we're going to add a type alias called remove pointer t that simply expands to type name remove pointer of t type in order to make usage for the client of our library way easier. Finally, we can static assert that remove pointer t of int star is the same as int. If we try out this code in the compiler explorer, you'll see that the code compiles successfully, proving that remove pointer t is actually doing what we expect. Remove pointer matches a t star and returns a t. A remove pointer t type alias is provided in order to reduce boilerplate. And the static assertion is using std is same v, which is available in type traits. This meta function takes a type t and a type u and returns true only if t and u are the same exact type. I just mentioned the header type traits, which we are going to explore in depth in the next video. For now, here's a sneak peek. Since C++11, the standard library provides this header, which contains a lot of meta functions that either manipulate types, such as std remove pointer or std make unsigned, or check properties of types, such as std is aggregate, std is copy constructible, is same, or is a value reference, and so on. This header is extremely useful when dealing with type transformations and checks, and we're going to see much more of it in the upcoming videos. Here's another way of defining the same remove pointer transformation by declaring a function template and then using decl type to inspect its return type. So in order to define that remove pointer meta function, you might just declare a remove pointer function that takes a t star and returns t. You don't have to define this function. Afterwards, you can create a type alias called remove pointer t that expands to the decl type of remove pointer invoked with declval of t. The idea here is that we are simulating a function call to this remove pointer function by passing some object of type t created using declval. And all we're doing is inspecting the return type of the function, which in this case simply gets rid of the pointer. Decl type of e evaluates to the type of the expression e, but the expression itself is not evaluated. std declval of t is a function whose return type is trefref. It is available in the utility header, and this function is not defined, it's just declared. And it's useful to simulate the creation of t instances in non-evaluated contexts, such as decl type. Note that std declval of t works even if t is not default constructible. Here's a common use case example. Imagine that you have a server class that takes a transport policy as a template parameter, and you store this transport inside the server class. Then, in the public interface, you expose a send function that takes some int and sends it through the transport policy. You also want to construct the transport passed by the server's constructor by a forwarding reference. So you will have a server constructor that takes a trefref, where this is a forwarding reference, not an r-value reference, which will initialize the transport data member by forwarding the passed value to the transport. So server transport stores a transport instance, and server's constructor takes a forwarding reference and then initializes the underscore transport data member. Now imagine that you want to use this server with some mock UDP transport layer, maybe for testing purposes. So you can create a struct called mock UDP that satisfies the transport interface, instantiate it, then create a server templatized on mock UDP, and pass the instance of your transport to the server. This works, but as you can see, we have some repetition as mock UDP had to be instantiated on its own and then specified as the server's template argument. To avoid this kind of repetition, let's follow what the standard library does for things like tuple, pair, or unique pointer, and create a make server helper function, which will deduce the template parameter for us. Here's what it looks like. This is a first possible implementation. Make server will take a transport by forwarding reference and then return a server passing t as a template argument and passing transport to this constructor. Now, if we try to use this make server function with an L value transport mock UDP instance, you would expect the type of the server to be server mock UDP. But due to the forwarding reference rules, this t here is deduced as a tref, as an L value reference. And when we are instantiating the server with t, we will actually instantiate a server of mock UDP ref, which is not what we want, as we want to take ownership of the transport layer. If we check out this snippet on Godbolt, you will see that in the main, we have the exact same code, and the generated assembly is annotated here, telling us that make server is taking a mock UDP reference, and that the server itself is templatized over a mock UDP reference. If we want to make sure that transport is either copied or moved into server, we need to somehow manipulate t. One way of achieving that is by using std remove reference t from the type traits header to remove the referenceness from the t type. In this case, the function is exactly equivalent as before, except for the fact that the server's template parameter is always deduced as a non-reference. In this case, if we use mock UDP t as a null value and then call make server of t, or if we use make server with an r value mock UDP, in both cases, the server will be deduced as a server of mock UDP without any reference in the template parameter, which is what we want because we want to own the transport layer inside the server instance. Here's the CPP reference page for std remove reference. It tells you that if the type t is a reference type, it will provide a typedef type, which is the type referred to t. Otherwise, type is t. This means that it will remove a reference if present, otherwise it will just return the exact same type you passed in. A possible implementation as seen below is a template struct that takes a t and specializes on tref and tref, always returning t as the type. So in these two cases, the reference is being removed thanks to this type alias. In this example, using a metafunction allows us to avoid code repetition thanks to perfect forwarding and a helper make server function, and ensure that the no references were accidentally stored in the server instance. As you've seen in the previous slides, we applied the remove reference t metafunction in place. This means that we're calling it directly where it's used. This is the recommended technique when dealing with one or two short metafunctions. Another technique that can help when applying more complicated metafunctions is using type aliases in a row. In this case, imagine that we have this complicated metafunction struct that internally uses multiple metafunctions. You can simply start at type alias step 0 with your first metafunction and then apply the subsequent one in another type alias that's going to be applied on step 0 and move on until you reach your final metafunction and simply call the type alias type so that it can be accessed from the user. Metafunctions are also really useful when coupled with variadic templates. Imagine that you want to create a tuple which decays every element type. In this case, you can simply create an alias called decay tuple that takes an arbitrary amount of types and then decays all of them by using this pack expansion over here inside the template arguments of a tuple. Now, if you use decay tuple with something like an int array and const int, you'll see that it's strictly equivalent to an std tuple of int star and int, as decay makes arrays decay to pointers and removes const and volatile qualifiers. Here's another realistic use case for metafunctions, converting C-string literals to std string. Firstly, we define a struct called toStdString that, given a type t, simply returns t. This is basically an identity metafunction. But we also specialize toStdString on the const char start type. In this case, we will transform it to std string. Finally, we supply a type alias in order to make usage easier for the final client. We might want to use this to create a tuple which automatically converts const star to a std string for us. In this case, it is sufficient to create a make myTuple function that takes a bunch of arguments and moves them into an std tuple that applies our previously created meta function into its template parameters. If we attempt to call this function with 10 and a string literal hello, you'll see that its type will actually be a std tuple of int and std string. This demonstrates that our meta function was actually applied on the hello string literal. This kind of technique is useful when you expect to mutate the passed string later on in the program, and you also want to make the interface as simple as possible for your user. And it can easily be expanded to match const and arrays. Also, references to const arrays, by simply providing another specialization that's templatized on a size tn and matches references to const and arrays. Note that std string is not a zero-cost abstraction over string literals, so only use this if you want to make your program simpler and you know that you're going to have to deal with std strings later on anyway. Here's a recap for this video. Metafunctions are functions that operate on types. They can be implemented using templates and type aliases. The standard library provides many metafunctions in the type traits header. They can be used to check properties of types or manipulate them. Here are my personal guidelines. Always provide a type alias for your metafunctions in order to simplify usage syntax. Decal type std decal val of t and std same v can help you implement and test your metafunctions thanks to static assertions. Use std remove reference t when implementing helper make functions for classes with a perfect forwarding constructor. Use metafunctions in the context of type deduction to streamline your interfaces and prevent surprising results. In the next video, metaprogramming utilities in the standard library, we're gonna take an in-depth look at the utility and type trait headers, and also some realistic use case examples.